In the 21st century, the battlefield has expanded beyond geography into an invisible ocean of electromagnetic energy that links sensors, weapons, and networks. And among the platforms designed to operate in that ocean, the EA-18G Growler occupies a unique tactical and strategic niche. The Growler is not primarily a missile carrier or a kinetic hunter, but a machine for shaping perception and denying an adversary the ability to see, speak, and guide its weapons when signals become the arteries of warfare. The Growler becomes the surgeon that clamps and redirects them. Born from the Super Hornet lineage, the Growler inherited proven aerodynamics and carrier compatibility, but it was fundamentally reconceived as a flying electronic warfare laboratory where high-power transmitters, agile receivers, and real-time signal processing converged to create effects in the spectrum. The program that produced the Growler answered a strategic requirement: how can naval aviation impose asymmetry upon adversary sensors and networks quickly and with reduced attrition? The answer combined mobility with electromagnetic power. Mobility allowed the Growler to fly with strike packages into contested airspace, and electromagnetic power allowed it to erase or corrupt the enemy's local picture. The result was a platform capable of performing suppression of enemy air defenses by means that rarely required kinetic destruction. The Growler's mission set maps onto contemporary electronic warfare categories. It performs electronic attack by generating energy and waveforms that overwhelm, confuse, or deceive radar receivers and guided munitions. It conducts electronic support by detecting and classifying emissions to generate actionable intelligence and targeting data, and it participates in electronic protection by shaping friendly emissions, managing deconfliction, and enabling resilient communications. The hardware that enables these functions begins with highly sensitive receivers. The EA-18 receiver system, for example, listens broadly across VHF through C-band ranges, capturing pulse repetition intervals, frequency, agility, and modulation characteristics that constitute a sensor's signature. The importance of early detection cannot be overstated because a radar's emissions are both a threat and an opportunity. Detecting a radar lets the Growler locate and prioritize targets and choose the most effective countermeasure. The offensive side is carried by jamming pods, historically typified by the EA-99 and being progressively replaced by the next generation jammer family, which uses solid-state architectures and digital beamforming to concentrate power into narrow lobes, thereby increasing effectiveness while reducing unwanted collateral effects. The transition from analog to digital transmitters has been transformational because it allows for software-defined waveforms that can emulate, deceive, or saturate across wide swathes of spectrum with rapid retargeting. The cockpit of the Growler is a human nexus where technical mastery meets tactical decision making. The pilot controls the physical fight, geometry, altitude, and survivability, while the electronic warfare officer curates the electromagnetic fight, selecting waveforms, managing dwell times, and deconflicting friendly emitters with lethal and non-lethal assets alike. The EWO operates with displays that present spectral heat maps, correlation tracks, and a prioritized emitter list. The crew's workflow is a continuous loop of detection, classification, engagement, and assessment. Much of the Growler's potency springs from its ability to link with other platforms and networks. A Growler does not operate alone. It integrates with carrier strike group, command elements, airborne command and control platforms, unmanned systems, and naval radars to create a correlated picture of the electromagnetic environment. When Growlers deploy, they provide both immediate suppression and a continuous stream of electronic intelligence that refines databases and waveform libraries used by the aircraft themselves and by higher echelon planners. Tactically, Growlers perform several distinct tasks. They lead suppression packages, opening corridors through integrated air defense zones by degrading early warning radars and fire control radars. They escort high-value airborne assets, providing a moving umbrella of denial. They support naval formations by creating electronic sanctuaries for carriers and amphibious groups, and they conduct stand-off or penetrating electronic reconnaissance missions to collect signatures and signal intelligence. In joint operations, Growlers have been paired with stealth aircraft that reduce the risk to the jamming platform and with unmanned decoys that expand the aperture of electronic effects. Historically, Growlers have been used in multiple theaters to deny adversary sensor functionality and to provide protection for coalition air operations during operations in the Middle East. Growlers performed continuous suppression and provided signal characterization data that directly improved the survivability of follow-on strike sorties. Their capability to force radar operators to choose between remaining blind or being targeted changed the calculus on the ground and in the air without necessarily destroying hardware. That intangible effect, behavioral modification induced by the presence of electronic warfare, is among the Growler's most important strategic returns, yet these strengths are balanced by critical vulnerabilities and operational constraints. High-power jamming is by nature detectable. Emitting energy into the spectrum creates signatures that passive long baseline arrays or direction-finding networks can use to geolocate the source. The Growler must therefore balance power and discretion, adopting tactics that include burst transmissions, rapid relocation, emission masking, and close coordination with escort and suppression forces to minimize exposure. The complexity of the threat environment has amplified as peer and near-peer competitors field more resilient sensors, cognitive radars, adaptive filtering, and machine learning-based signal processors reduce the window of opportunity for traditional jamming techniques. These systems can maintain track through interference or reconstitute their picture quickly, forcing the Growler community to develop more sophisticated schemes that combine deception with denial and exploit timing, geometry, and spectral nuance. The evolutionary contest between jammers and sensors is essentially a software battle paced by hardware limits, but decided in code and tactics, which demands a continuous cycle of upgrades and feedback loops. From operations to engineering, the engineering and logistical tale that sustains Growler operations is both technical and doctrine-heavy. Unlike traditional aircraft, whose sustainment is measured in rounds and fuel, the Growler's readiness depends on waveform libraries, software integrity, cooling, and RF component reliability. Waveform development requires secure data pipelines from signal intercept units, post-mission analysis labs, and intelligence centers. The deployed units the ability to rapidly push new waveforms and signature updates to aircraft and theater can make the difference between success and failure in an evolving threat environment. Additionally, RF transmitters and sensors are sensitive to maritime environments. Salt-induced corrosion, thermal cycling, and vibration can degrade antenna patterns, receiver sensitivity, and transmitter output, necessitating regimented maintenance cycles. And environmental conditioning sustainment also requires a specialized training pipeline. The electronic warfare officer must become proficient in signal theory, radio frequency propagation, antenna patterns, emitter behavior modulation recognition, and real-time tactical decision-making. Training regimes combine classroom theory, live emitters, simulation, and adversary emulation ranges where EW tactics can be tested under controlled conditions. The human element extends to intelligence analysts, software engineers, and maintenance crews who together form additional sorties. Strategically, the Growler alters deterrence and escalation dynamics, a force capable of reliably denying an adversary the ability to detect incoming formations or to coordinate effectively. Can create leverage that prevents kinetic escalation because the threat of being rendered blind and disorganized is itself a coercive instrument. This kind of influence often acts below the threshold of open conflict, but can decisively affect bargaining positions during crises. However, spectrum control has ethical, legal, and geopolitical dimensions because electromagnetic effects can impact civilian infrastructure, communications, navigation, and even economic systems. Increasingly rely on shared frequencies, and aggressive jamming in a contested theater risks harming neutral or civilian networks. The rules of engagement for spectrum operations therefore incorporate legal counsel, interagency coordination, and often diplomatic considerations to avoid unintended second-order consequences. On the technical horizon, several trends promise to transform how Growlers operate: the adoption of digital radio, frequency memory, waveform libraries, machine learning analyzers, and distributed cooperative jamming architectures will increase both the speed and precision of spectral effects. Digital beamforming and active electronically scanned arrays permit highly directional energy projection, reducing signature and collateral interference while increasing range and resilience. Equally important is the integration of unmanned systems as adjunct electronic warfare nodes. Unmanned platforms can carry expendable or persistent jammers close to contested areas or form a network cloud of emitters that complicated targeting and increase the survivability of manned growlers. Another major development is the move toward joint multi-domain electromagnetic operations, where naval growlers are nodes in a larger system that includes space-based sensors, cyber effects, ground-based EW units, and alliance shared databases. The intent is to create a singular electromagnetic picture made of layered sensors and effectors that can be tasked dynamically across services. The practical implication is that a growler in such a network does not simply jam, it contributes to and uses a theater-wide understanding of emissions to select effects that achieve mission objectives with minimal collateral impact.